All right, guys, welcome back. This is going to be the 6.2 instructional video. If you haven't watched 6.1 yet, or you weren't here for it in class, go back and watch that video first. It's going to review the concepts of slope. And in 6.2, we're going to introduce our first of three forms of linear equations. Chapter 6 is all about linear equations. There are three different forms we see this for algebra. We're going to examine the first of the three today. But first things first, let's talk about what will the graph of a linear equation look like. We can play a little hangman with this. Okay, but what is it going to look like? It will look like a line. Okay, the graph of a linear equation is going to look like a line. And this should make sense. Why? Well, think about the word. What is the root of the word linear? It is line. Okay, so the graph of a linear equation, all linear equations are going to create lines. Now, this first part of the lesson is going to be more traditional, definition oriented. We want to get a grounding in the idea of our first form of a linear equation. Then we will dive into some specific practice and what I want you to be able to do. So first things first, linear equations are equations containing two variables that produce a straight line when graphed. Linear equations are equations containing two variables that produce a straight line when graphed. Again, we see this concept of a linear equation is going to produce a graph of a line. If an equation is graphed and it is not a line, it is not considered a linear equation. Now, what are the features of linear equations? Well, the first one is they contain two variables. Okay, so when we're identifying, hey, is an equation linear, what we want to think about is an equation that has two variables. Now, the general form of linear equations that we're going to look at, they will obviously have more than one variable. I'm not referring to those. What I'm referring to is when we are looking at a specific equation with numbers plugged in, are there two variables present? Okay, are there two variables present? We don't. The second criteria, each variable must have a power, aka the exponent, equal to 1. Okay, you cannot have a power greater than or less than 1. Okay, power equals, aka the exponent, must equal 1. Must equal 1. So some examples we can think about. I'm going to write up here 4 to 5 linear or potentially linear equations. I want you to identify to yourself which are linear equations and which are not. Okay, so we're going to dive into which of the following are linear equations. Okay, so take a second and see if you can figure it out. Well, each one we want to look at, and what we can imagine in our brain is, one way of thinking about it, we look at this and go, okay, if I graphed this, would it produce a straight line? Would it produce a straight line? Actually, I'm going to make a slight edit here. I'm going to change these variables. H and T. Okay. Z can get a little confusing. You'll understand why if you get to higher math. But for our two variables, I'll use H and T. But what we're going to do is we want to imagine these when graphed, that when graphed, they will produce a line. So that's one way of thinking about it. But the other way is let's think about these two features that we know of linear equations. They can only have two variables, and the exponent must be equal to 1. Okay, so I look at the first one. Does it have two variables? Yes. We see a y and we see an x. Both have powers of 1, so is this a linear equation? Yes, it is. Similarly, we look at the second one. While we don't see a y and x, it still has two variables, both to the first power, so this is, in fact, a linear equation. Because students in algebra work so much with the variables y and x, it can get tempting to think, oh, it's not y and x, can't be a linear equation. Well, that's not true, and in fact, a lot of the real-world problems we're going to work with, we're not going to use the variables y and x, right? The reason I chose h and t, maybe here we're looking at height and time, okay? We're looking at height and time as our variables, okay? Either way, we've got two variables, both to the first power, so it is a linear equation. The third one, though, will not be a linear equation. While we meet the two variable criteria, we have an exponent here that is squared. The y is squared. This would not be a linear equation, okay? We're going to skip over the fourth one for now. Now, the last two, really the last two, are both challenging. I'll start with the fifth one. You may be tempted to think, well, hey, that y is to the first power, and so is the x, and there are two variables, and we do meet the two variable criteria. But in fact, this would not be a linear equation. This is a little challenge problem, a preview of chapter 8 when we will learn about exponents. And what you learn when you learn about exponents is that if the variable is ever in the denominator of a fraction, it is equivalent to a negative exponent. This is actually y to the negative first, which again, that power is not equal to 1. If you don't believe me, if you graph this, you would in fact not get a straight line. Now, what about y equals 0? Well, the temptation is to go, while the power is equal to 1, there are not two variables. But that's slightly, it's still, if you would graph this, you would see a line. So how do we rectify this? How do we justify this given our criteria? Well, just like when you were a little child, and when you were a child, whenever you didn't see the sun, you thought, oh, the sun's not there. But as you grew older, you recognized, well, the sun's still there, it's just behind the clouds. Similarly, there are two variables present here. We just can't see one of them. Namely, we can't see the x variable. But how do we know it's there? Well, just like I would write 3 plus 0, we grew out of that and said, well, we don't need to write plus 0. We just write it as 3 because adding nothing will leave us with 3. Similarly here, we can imagine that here there indeed is an x present. There are just 0 of them. There are just 0 of them. So this is, in fact, a linear equation. Now, we typically just write y equals 0, or maybe a better example is if we think about y equals 2. The 0 does work. If we think about y equals 2, we just will say y equals 2. Even though there really is an x here, there are just 0 present. And this is why, if you graph y equals 2, you will see a straight line. It is a linear equation, okay? And we'll dive into more of what that looks like earlier. I think we looked at an example of a graph. It actually produces, y equals 2 produces a horizontal line, but we'll dive into that more in later sections. Okay, so broadly speaking, how do we figure out whether something is a linear equation or not? Well, the two criteria we're going to look for is, are there two variables, and are the powers of those variables 1? The predominant form you're going to see these in will be these two. Stuff with exponents, whether positive or negative, we'll learn about in later chapters, maybe even later subjects of algebra. So we've got a basis in linear equations now. The question is, how do we write linear equations? And you're going to learn in the next 3 sections that there are 3 different ways of writing linear equations, algebraically speaking. The first that we are going to learn about is slope-intercept form. Slope-intercept form. What is slope-intercept form? Well, it's one of the most famous algebraic equations out there. Y equals mx plus b. y equals mx plus b. This is the general form. When we see specifics for specific lines, we will have numbers plugged in for m and for b. So you do not need to fret thinking, oh, there are 4 variables there. There's no way that produces a line. Well, when we plug in our specific values for m and b, we'll be back to that 2 variable criteria for specific linear equations. So the general form, y equals mx plus b. M is going to be your slope, and b is going to be your y-intercept. And again, I'm not going to spend a ton of time talking about slope here. Slope we addressed in 6.1, so if you want to go back and watch that video, go for it. We will address what the y-intercept, though, is. Okay, and the common way I would describe this to people, if you don't know what an intercept is, I want you to think about what an interception is in football. What happens in football? Well, an interception is when one team is passing the ball and a player on the other team catches it and they run the other way with it. Effectively, the ball has switched teams. It has switched sides. Okay? The possession of the ball has switched sides. Well, that idea of interception carries over to the y-intercept. What happens? Well, the y-intercept is where a line, the graph of a linear equation, switches sides. Specifically for the y-intercept, it is where the linear equation switches sides of the y-axis. In the visual here below, my red arrow points to where the y-intercept occurs. This is where the linear equation switches sides, crosses over the y-axis. We also will discuss in later sections the x-intercept, which is again where a linear equation will cross the x-axis. Okay? That's not the y-intercept. This will be the x-intercept. And again, we'll address that later. But for slope-intercept form, we need 2 things. We are going to need to know the slope, and we're going to need to know the y-intercept. Okay? Now, in any given linear equation form, will you know the slope and the y-intercept? You won't always know that. And in those cases, we will work with other forms of the linear equation better suited to it. But when we do possess a slope and a y-intercept, we are going to use slope-intercept form. So enough definitions for now. Let's get into some practicality. Let's get into, okay, Mr. Carter, you're throwing all these things my way. How do I know if I'm getting it or not? Well, let's dive into some problems and see where you're at. We're going to start small. So for these 2 problems, what I want you to do is, given the linear equation, that linear equation being in slope-intercept form, I want you to identify the slope and the y-intercept. Okay, hopefully you've taken a chance to do that. And it's helpful in order to solve these to always remember the general form of slope-intercept form. If you don't have this committed to memory, this would be a great time to do so. It's going to make your mathematical life in algebra immensely easier. So I know slope-intercept form is y equals mx plus b. I have a linear equation in slope-intercept form right here. And I'm to identify the slope and the y-intercept. Well, I know the slope is represented by the letter m. And I know, let's stay consistent here, I know the letter b represents the y-intercept. So looking at my equation, I see that the slope is 3, and the y-intercept is -5. Slope is 3, and the y-intercept is -5. Similarly, in the problem below, identifying the slope and the y-intercept, the slope will be -2, and the y-intercept will be +1. Okay? We always remember in slope-intercept form, the slope will be the number or fraction attached directly via multiplication to the x variable. The y-intercept will be the constant. So now let's go the other way. I will give you the slope and the y-intercept. You go ahead and write an equation in slope-intercept form. Well, again, we know slope-intercept form is y equals mx plus b. So the question becomes, what is our slope? Well, in this case, we see the slope is 3/8. The slope is 3/8, and the y-intercept is 6. So my linear equation, given that slope and given that y-intercept, will be y equals 3 over 8x, 3 over 8 times x plus 6. Similarly, in the problem below, y equals negative 3x plus 4. Okay, very basics of slope-intercept form. By the way, I know I'm going somewhat quickly through these. I think these are a review for most of you. If they're not and you're stuck, though, feel free to email me. Now let's transition to the next level. Here we now have a graph, and given that following graph, we want to write the equation of a line. Okay, we're advancing to the next level. So again, try this on your own, and then I'll solve it. So pause the video, try it, and then check your work with me. So hopefully you've given it a shot at this point. So when I'm looking at this, I see a few things going on. Again, when I see write the equation of a line, right now, though we'll learn more, the only equation of a line I know is y equals mx plus b. This is the general equation for a line. It's the only one I know. Okay? And I know that in order to write that equation, I need two things. It's like a recipe. I need my slope and I need my y-intercept. Okay? In order to formulate my equation of a line, I must have my slope and my y-intercept. Again, we will learn other forms at later dates where you don't necessarily need the y-intercept specifically, or you don't need maybe the slope directly. But for now, our equation of a line is y equals mx plus b, and it requires a slope and a y-intercept. So I look at this graph here, and I observe that the y-intercept, I know that's where I cross the y-axis, where I switch sides. That occurs at the point 0, 4. At 0, 4. So my y-intercept, y equals blank times x, plus my y-intercept will be 4. Now the question becomes, what is my slope? Well, we know with graphing that in order to find the slope, we talked about this in the previous section, one of the best ways to do it is rise over run. Rise over run is one of the best ways to find our slope when we're working with graphs. So there are different ways I could do this, right? Maybe my gut tells me, well, let's try going down 1. But the problem with only going down 1 is if I'm going to go over, you can see on the grid here, I don't know where that is. Specifically, I don't know the x value. Okay, I went down 1, so my slope is 1 over, I don't really know. I don't know my run. Is that 0.6? Is that 0.5? Is that 0.7? I don't really know. So that's not going to work. So maybe I progress down a little bit further. Well, I go down 2, and again, I'm going to run into the same problem. If I try and go over at y equals 2, I'm going to go over 1.3? I don't really know. What you want to do is you want to find a solid rise over run where you go, I'm going down this many, over this many, and it puts me here. Okay? So here I'm going to keep going. I'm going to go down 3. And here, now, I can go over exactly 2. And I know I'm going to run right into that line, okay? On the grid, I'm going to earn it right into the line. If I go down 3 over 2, I'm going to hit a point that I know is on the line, okay? Down 3 over 2. This point being 2, 1. This point being 2, 1. Okay, so I went down 3 over 2. If I wanted to confirm that, I could keep going. If I go down 3 over 2, hey, I hit another solid whole point on the graph. And it's not that these other, intersections, there are infinite amount of points on a line. I could go down 1 and over so many, and that will lie there, but I don't know what that is off the top of my head. But I see that, hey, I'm going to hit solid points on my line, whole numbers, if I go down 3 over 2. Okay? So going down 3 over 2, how do I write that? Well, I'm going rise, which is minus 3 because I'm going down, over 2, and that will be my slope. Minus 3 over 2 is my slope. Okay, so it's putting those two ideas together. My y-intercept is at 4. My slope, I go down 3 over 2. Down 3 over 2. So my slope will be minus 3 halves x plus 4. And again, I think thinking about that fraction is the easiest way to think about it. Could we simplify that fraction? Sure, we could say, maybe we say minus 1.5 over 1. Minus 1.5 over 1. We could say that. But again, I think the easier fraction to work with is minus 3 over 2. Okay? So this is how we can use our knowledge of slope-intercept form to write an equation of a line given a graph. As long as we have a y-intercept and a slope, we're okay. Well, now let's go the other way. Now we have an equation of a line. Let's go ahead and graph it. Now, when we're thinking about this equation of a line, I'm going to go over by ones, and I'm going to go up and down by ones, by the way. But in the interest of time, I'm not going to write out all the numbers. Now, what we used to have to do to graph things is we would have to plug a bunch of different x values into this equation and find the matching y's, right? I would plug in 0, 1, 2, 3, find the matching y values, connect them with some dots. But now that I understand slope-intercept form, all I need to do is I can identify the y-intercept and then just work with my slope from there. Well, I know the general form of a linear equation in slope-intercept form is y equals mx plus b. And so I know b being my y-intercept. In this case, my y-intercept is going to be minus 1. My slope in this case is going to be 3. Now my starting point, since I know that specific equation of a line is going to go through the point 0, -1, since the y-intercept is minus 1, I want to find at least one other point I know the line will go through so that I can connect it and display that line. I see that the slope is 3, and any whole number can be written as a fraction over, if we put the whole number over 1. And why I will put it over 1 is then it makes my rise over run really easy to see. What I'm going to do is, with this slope of 3, I'm going to go up 1, 2, 3, 1, 2, 3, 1, 2, 3, over 1. Up 1, 2, 3, over 1. And we can see our line develop. To graph a line, we have to have a minimum of 2 points, and we connect them with the line. So how do we graph equations in slope-intercept form? Well, you're going to plot your y-intercept. Then you're going to use your knowledge of slope and rise over run to identify 1, 2, minimum 1, but usually a couple other points, and connect them all with a line. Guys, thanks for watching. I hope it makes sense. Let me know what questions you have.